First of all, I'd like to thank the organizers for arranging this conference and also for giving me the opportunity to present our work. So my talk today will be about pitfalls of the proof of work protocol, and it's joint work with my advisor, Agostino Capponi, who's also from the Industrial Engineering and Operations Research Department at Columbia University. So since Bitcoin was developed in 2009, it has experienced a rapid increase in value. As of this month, May 2019, the market capitalization for Bitcoin exceeds $100 billion, making it the most successful in more than 1,500 cryptocurrencies out there. This success of Bitcoin has attracted a lot of research from many researchers, many of which are in the audience right now. So, in the interest of time, I will not go into the literature review in detail. I'll just go briefly through it. So, one strand of literature that studies cryptocurrency took or studied blockchain as a general purpose technology and its use in market design. Another strand focused on Bitcoin valuation and pricing. Basically, they tried to find the specific features that determine the cryptocurrency price. Another strand of literature focused on optimal design of cryptocurrencies and sustainable alternatives. So our work is more related to this last strand of literature, which studies Bitcoin operations. Basically, we focus on the miners and their decisions in Bitcoin. So let me give you some background information. At the heart of Bitcoin is the blockchain, which is a completely decentralized digital ledger where transactions are publicly recorded. Since there is no central authority in the blockchain, it relies on a network of nodes or computers to verify, update, and store transactions. In order for these nodes to incur the costs of updating this ledger, they need to be incentivized. They need to be given an incentive to do these tasks. This is done through a process called mining. So in this process, these nodes, which we will refer to as miners, compete to solve a computationally difficult problem, which is known as the proof of work protocol. The first miner to solve this problem gets to update the ledger. If a miner gets to update the ledger, then he's rewarded with newly minted coins, and he gets to keep the transaction fees associated with the transactions that he records in a specific block. So, Nakatomo, the inventor of Bitcoin, envisioned a completely decentralized system in which mining can be done by practically anybody using off-the-shelf computers. However, as Bitcoin value increased, as the price increased, firms started to develop more efficient mining hardware. By developing more efficient mining hardware, they're able to exert a higher computational power, and this would increase their probability of mining a block and getting a reward. As a result, mining became unprofitable for individual miners. Instead, mining became increasingly vertically integrated, with single firms designing chips, maintaining them, and operating data centers. For example, Cheng reports that Bitmain, a major Bitcoin mining hardware manufacturer, is opening mining farms in Canada and Switzerland. This is in addition to the mining farms that it already owns in China. K3 states that Bitfury, another major Bitcoin mining hardware manufacturer, is opening a network of Bitcoin mining operations in Paraguay. This is in addition to the mining centers that it already owns and operates in Canada, Norway, Iceland, and Georgia. So, given these transformations in the mining industry, does the proof of work protocol still enable and support a decentralized payment system? So answering this question is critical because the whole point of introducing cryptocurrency is to have a decentralized payment system. So just to give you a preview of our results, we show that just by having the proof of work protocol, the proof of work protocol drives the mining industry or helps drive the mining industry towards centralization. We also show that it also leads to an arms race in research and development between firms. And due to this arms race, all firms are worse off. So let me explain our model. So we consider a stylized model. You have capital N firms, and we consider a two-period or two-stage time horizon. In period 1, each firm must choose a research and development level, which we denote by small xi. We assume that the research and development costs are quadratic. So the fact that the research and development costs are quadratic with a coefficient of gamma. The assumption that the research and development costs are convex is meant to capture the diminishing returns to scale property of research and development. In the second stage, each firm must choose a hash rate, which we denote by hi, small hi, that's used for mining. So the hash rate is the technically correct term for the computational power that I was referring to in the introduction. Basically, hash rate refers to the amount of guesses you're making at a given second. The higher the hash rate, the higher the number of guesses you're making at a given second, the higher your probability of mining a block and getting the rewards. We assume that the hash cost function is linear and is given by this specific form. So alpha is the initial marginal hash cost prior to any research and development. The more you do research and development, the lower is your marginal hash cost. Once all firms specify their hash cost, the rewards for each firm is specified by this function here. Firm's I share of the reward is given by this function. Hi is the hash cost, is the hash exerted by firm I. Capital H is the total or aggregate hash rate exerted by all firms in the game. And R is the total reward that can be obtained from the mining stage. This includes rewards from newly minted coins and transaction fees. So basically, this reward function captures two key properties of the proof of work protocol. First of all, your reward is proportional to the amount of hash rate that you exert. And this is related to the intrinsic property of the hash function. The more hashes you do, the higher the probability that you're gonna mine a block and the higher the reward that you're gonna get. The second property that this revenue function captures is that regardless of the total hash rate exerted in the system, the total reward that can be extracted in the second period is fixed. And this is meant to capture the dynamically changing difficulty level of the Bitcoin system, which makes sure that the amount of Bitcoins that can be mined at a given period of time is fixed. The objective of each firm is to maximize its individual second stage mining profits, net of its first stage research and development expenditures. So we solved this game using backward induction. We solved for the subgame perfect equilibrium. First, we assume we have a given research and development profile, and we characterize the hash rate profile. Using this characterization, we solve for the subgame perfect equilibrium of the full game. So let me give you some results. So now we will focus on the second stage game, where we fix the research and development levels for each firm. So we do not by boldface X the research and development profile for all firms, and small c of I is the marginal hash cost. So small ci is basically just the derivative of the hash cost function. So the first result that we get is that for any research and development profile X, there exists a unique equilibrium hash rate profile. Moreover, if all firms are active in that equilibrium, then the equilibrium hash rate can be given in closed form, which is given by this function here. So the important thing to learn or to extract from this function here is given by the following corollaries. First of all, the activity of a firm, whether or not a firm is active or not, and the fraction of hash rate that it controls or it contributes depends solely on the cost structure and not on the revenues obtained from mining. This may sound a little bit counterintuitive, since suppose I'm not active in mining because the rewards are much lower than the cost I have to put to mine the rewards. If Bitcoin price increases, then it should be profitable for me to enter and mine. However, this is This is assuming that other firms, my competitors, will keep their hash rate constant, but this is not the case. They will also increase their hash rate, and so this will drive me out of business again. So the second point that I'd like to point out is, so I'd like to state it in more informal terms. This basically says that if your per unit hash cost is just a little bit above average, then you will not be active. You will go out of business. So let me give you some examples. If there are just 10 miners, 10 active miners, then any firm with a per unit hash cost that exceeds the average cost by just 11% will not be able to compete. He will go out of business. If there are 20 miners, then any firm with a per unit hash cost that exceeds the average by just 5% will go out of business. And this results specifies the tendency of Bitcoin mining towards centralization. It also shows the importance of research and development in being competitive in the mining stage. Without developing more efficient mining hardware, you can easily be pushed out of competition. So let's move to the full stage game. Suppose gamma is large enough. Remember, gamma is the coefficient in the quadratic research and development cost function. If gamma is large enough, then there exists a unique symmetric subgame perfect equilibrium, and this subgame perfect equilibrium satisfies these two properties. First of all, an increase in mining reward increases the equilibrium research and development level and the total hash rate in the system. So this result is intuitive and it's consistent with empirical evidence. For example, when Bitcoin was first introduced, mining was done using regular CPU. As Bitcoin value or price increased, people started to develop more efficient mining hardware, moving to GPU, to FPGA, to even more specialized ASIC, and who knows where we'll be in the future. The second point is that in this equilibrium, all firms invest a strictly positive amount in research and development. So in order to assess whether or not this outcome is good, we compare it to the situation where firms cooperate. So this is the benchmark that we're going to use to assess the efficiency of this outcome. So we consider the case where firms cooperate in the research and development levels, but they remain competitive in the second period or in the second period hashing stage. So in period one, firms choose their research and development profile X to maximize the total profit, which we denote by capital pi of X. Solving this, you can find that there exists a unique symmetric equilibrium for this cooperative research and development at which firms will agree not to exert any research and development in this specific game. So this result basically says that in the non-cooperative case, firms are exerting an excessive amount of research and development. So to understand why this happens, we study how firms are making their decisions in the cooperative case. So in the cooperative case, each firm would like to choose its research and development level xi to maximize the sum of profit, which is given by capital pi of x. Solving for the first order conditions, you get this expression here. So the first term is the marginal revenue, the marginal profit that you get from your own investment in research and development. This term is captured in the non-cooperative case. I would like to maximize my profit using my research and development decisions. However, the second term represents the externality confirmed by firm I research and development levels on all other firms. This externality is not internalized in the non-cooperative case, but it is internalized in the cooperative case. This externality turns out to be not only negative, but it exceeds the positive effect that the firm has on its own. The basic intuition why this holds, why this negative externality exceeds the positive externality of your own effect is because of the proof of work protocol. Basically, aggressive competition induced by the proof of work protocol prevents firms from capturing the surplus from the research. So what can we do to improve the situation? What can we do to reduce the arms race between firms? In the next couple of slides, we will show that promoting spillovers, promoting research and development spillovers would improve the outcome in the non-cooperative case. So research and development spillovers occur when firms have difficulties protecting their intellectual property. Channels from which the technology can spread include the transfer of employees in between firms, informal communication between the network of engineers. The input supplier can leak some information about competitors. So to account for spillovers in our framework, we use this generalized cost function. Basically, the first two terms is exactly the same as we had in the original model, and we incorporate this extra spillover term. Beta, we refer to beta as the spillover parameter. Beta ranges between 0 and 1. If beta is 0, then there is no spillovers, and it reduces to our old basic model. If beta is equal to 1, then this corresponds to a research joint venture in which all research findings are communicated between the firms and are shared between them. In reality, the beta parameter is in between these two extreme values. So what happens if the spillover parameter is increased? First of all, an increase in the beta parameter decreases the research and development level for any firm and improve profits. So this can be intuitively explained using the free rider effect. If you increase beta, then firms would tend to free ride on others. I wouldn't want to spend as much money on research and development because I'll just take it from other firms. So this is good in the sense that it improves profit and reduces the research and development level for firms. However, one might argue that this is not necessarily good because reducing research and development may also reduce the total hash rate exerted in the Bitcoin system. And the total hash rate exerted in the Bitcoin system is an important security measure for Bitcoin because it protects it against external attacks. So while it's true that absence of spillovers maximizes the research and development level, it does not mean that absence of spillovers also maximizes the total hash rate exerted in the system. The reason is that hash rate is proportional to the effective research and development and not the individual research and development done by firms. So the effective research and development takes into account both the research and development level that I personally do and the amount of research and development that spills over to me from other firms. It turns out that the effective research and development or spillovers has a non-linear effect on this effective research and development. On the one hand, increasing spillovers increases the effective spillover parameter because firms benefit from spillovers obtained from other firms. On the other hand, as we showed in the first part, increasing research and increasing the spillover parameter reduces incentives for firms to invest in research and development. It turns out that if the spillover parameter is initially, if the spillover parameter is very low, then the positive effect dominates the negative effect of the spillovers. And so initially, as you increase the spillover parameter, the total hash rate increases until you reach a threshold, after which the total hash rate starts to decrease. So the bottom line of this slide is to show that promoting research and development is good to reduce the arms race between firms, and it improves firms' profit without compromising the security of the Bitcoin system because the total hash rate can also increase because of this increase in spillover parameter. So how can we increase the spillover parameter? What can we do to promote spillovers? One thing is that we can make patents more difficult to obtain in this specific technological sector. Developing more efficient ASIC equipment. If patents were more difficult to obtain, then more information would be able to spill over between firms. This intellectual property is not protected for a specific firm. It can transfer to other firms. Another point is we can ban the use of non-compete agreements in this also technological sector. This would promote the flow of employees between firms and increase the spillover parameter. So let me recap the results that we present. First of all, we show that the proof of work protocol induces an arms race between firms. We show that spillovers can be used to reduce or mitigate this arms race and get closer to the efficient solution or cooperative efficient solution. So the arms race can be somewhat mitigated or reduced. However, the main point or the main difficulty is in the tendency towards centralization, which is a more critical issue because the whole point of introducing cryptocurrency is to have a decentralized payment system. So this issue is more drastic and needs further look into it. One possible solution is to use a different protocol, for example, the proof of stake, proof of burn. There are many different protocols that we can test out, but again, more research needs to be done in these specific protocols to understand better how, if they have other problems that also needs to be mitigated. And thank you for your attention.
Excellent timing, congratulations. We have time for 2 questions. I said 2. Okay, because I interrupted you so many times. It's better.
So maybe I missed it, but all of these research results, the vector of n results, how do you store them?
So what do you mean by the vector of n results?
So everybody is participating in this research. Everybody has some results. You need to store it so that we will know who to reward, even later. Right?
So in our framework, in the first stage, maybe I was clear. In the first stage, firms are developing more efficient mining hardware. They're developing it for themselves. If you develop more efficient mining hardware, then you can do the hashing in the second stage game at a lower cost. So the whole point in doing the research and development is to improve your hashing cost and to give you an advantage in the second stage game so that you can mine more bitcoins and gain more money. Does that answer your question?
Not completely, but I'll let others.
Hi. Okay, I have 2 questions. So one is related to the mining pools themselves. So everybody talks about the mining pool as if they were firms that act strategically, but and you said they own the mining farm, but to me it's completely unclear that's what happened. But I mean, everybody can join a mining pool. They are more diversifying way to, so I can buy some hardware and join any mining pool. Actually, I can join all the mining pool. It's no problem. And do you have any evidence that the mining pools themselves own the factories, or maybe you have factories that actually I know they are mining and they are not belonging to any mining pool, and then they join mining pool exports and join many of them. So it's not completely clear that they are firms that invest strategically in their hash rate. And my second question is related to the innovation. So what type of innovation are you talking about? Because there is an innovation in the sense that I can spend less electricity, but in terms of mining technology, most of it is embedded in the ASICs. I know that people say that there is ways to divide the hash table and so on, but it's not really documented. So anyone can buy an ASIC online and start to mine, and actually people are doing it, and they are competitive. So if there was so much R&D, nobody would find it profitable to buy an ASIC online on Amazon and run it from his basement. So it's not super clear to me that besides the cooling technology and the electricity, that there are much innovation in the mining technology per se. Or maybe you have some evidence on that. So that was my 2 questions.
Yeah. Regarding your first question, regarding mining pool. So in our talk, we do not refer to mining pool at all. We're referring to individual miners which can use their power in any pool. So the reason why we don't refer to mining pools is because suppose you have a big miner which controls 50% of the power. He can easily just segregate his power among 3 mining pools and name it. So our focus is on individual miners, those that actually make the mining, not actual mining. You mean the miners themselves? So our paper is based on the fact that there are, so you don't know exactly how much there are hundreds or thousands. So some papers, they show that 60% or 70% of the power is controlled by large data centers. Who actually controls these data centers is not very clear. Our view, we see that it's 20 or 25. I don't see them as more than 100.
So,
Last question.
so it's more of a comment. So I completely agree with what you're saying. And to answer your question, what happens is that yes, you can buy mining hardware, but it will be obsolete because these firms that manufacture mining hardware, they first use it, and when it becomes unprofitable for them in the highly competitive setting, they sell it on. And the reason it's profitable to you, I don't know any of you ever tried mining recently, it's only profitable if you actually have a use for the excess heat. So if you're living in a cold country and part of your mining heat goes towards reducing your heating bill, then yes, it's profitable to mine because you're also heating your apartment from your basement. And that's the only way, or you're stealing electricity, that's the other way it can be profitable. But but those are special cases, and that accounts for what you say about 40% of mining, and 60% of mining is done by freshly manufactured cutting-edge mining hardware ASICs, which use the least amount of energy to produce the hashes. And if you're only competing on electricity cost when you're honestly paying for your electricity bills, there's no way you can compete with them.
Thank you very much. So I think we have to go to the next paper. Thank you very much.
Thank you.